Chase, I'm not sure you know that you're muted.
Sorry, everyone, I was muted. Welcome to Astronomy Live, off to a little bit of a rough start, but we'll get going in a sec. We're waiting on people to trickle in. We have some talks coming up for you, and we are going to do some trivia as we wait for people to trickle in. Go to menti.com. The code is 1932774. Give me 1 second to try and get this going. All right, we've got 4 contestants so far, so let's get started. If you join late, that's no problem. You can join at any time. All right, first question. The asteroid belt in our solar system is situated between which 2 planets? Is it Neptune and Uranus, Earth and Venus, Mars and Jupiter, or Jupiter and Saturn? So even though, oh, okay, we got it. Mars and Jupiter. All right, 3 people got that right. Let's go on to the next question. All right, question 2. About how fast is the International Space Station traveling around the Earth? Oh. Sorry, it's gonna go. Okay, so again, how fast is the International Space Station traveling around the Earth? Is it 8,000 miles per hour, 18,000 miles per hour, 28,000 miles per hour, or 38,000 miles per hour? I can tell you it is less than 0.03% of the speed of light. All right, most people got that right. That's impressive. All right, let's check where how the leaderboard stands. We've got Cake, Tom, and Shammy right out in the front. Well done. Let's see if those leads will hold. All right, everyone. Just a reminder, we are about to get started with Astronomy Live. We've got some great talks coming up. But in the meantime, we're doing some trivia. If you want to join, it's not too late. Go to menti.com, code 1932774. It's at the top of the slide. If you enter it, you can join trivia on either your phone or your computer. All right, let's go to question 3. How many Earth years does it take Neptune to orbit around the sun? Is it 6.5 years, 65 years, 165 years, or 265 years? One hint may be that Neptune orbits about 30 times as far away as Earth does, but only if you're super quick with Kepler's law will that actually be useful to you. All right, you got answers pretty much across the board, but yeah, most people got it correct. Good job. All right, question 4. Which planet in our solar system has the highest mountain? Is it Neptune, Venus, Mercury, or Mars? This mountain is basically 13 and a half miles high, which makes it about 2.5 times the height of Mount Everest. I think most people will get this one. Yes, all right, 5 people got it right. Good job. Okay, let's take one last look at the leaderboard before our final question. Oh, Cake has managed to just hold on to their lead with Clippy right behind, Bill, and then Shani. And then Binky, Simba, and Gary too. All right. One last question. We will have more trivia coming up in between the talks. So this is not your last chance for glory. What color are the sunsets on Mars? I think this is a beautiful question. Are they blue, orange, green, or red? Even though Earth and Mars share the same sun, it does not mean that their sunsets are the same color. That is set by the composition of the atmosphere. All right. Oh, answers across the board. All right. Most people were tricked. Oh, answers across. Sorry about that. I have muted the YouTube stream. Okay, great. So that is the last of our trivia. So now I'll ask our speakers to come on so they can introduce themselves. And I will stop sharing. Welcome. All right, so we've got some great speakers for you today. My name is Chase. I was doing the trivia pretty ineptly, but I'm a grad student at Northwestern, and so not a professional trivia master. My job is working with LIGO to detect gravitational waves and learn about black holes and neutron stars and how they emerge. How about you go next, Charlie?
Hi, I'm Charlie Kilpatrick. I'm a postdoctoral fellow at CIERA at Northwestern University. I study mostly supernovae and their progenitor stars, which I'm about to talk about, but also gravitational wave sources and fast radio bursts.
Thank you. And how about you, Alex?
So my name is Alex Garvich. I'm a PhD student at Northwestern. My time is split between making internet memes and researching star formation in galaxies with supercomputer simulations, which I am going to tell y'all all about in the second talk tonight.
Awesome. So we're going to start with Charlie. Before we get started, though, I want to shout out Carrie and Alicia in the chat and behind the scenes, as well as Deanne helping to write trivia. And then a big shout out to really the person who got this all started, Gretchen Olschlager. She is moving on to bigger and better things outside of Northwestern, but she'll forever be a part of the DNA of Astronomy Live. So we owe her everything. I hope you're watching either now or sometime in the future, Gretchen. All right, great. So Charlie, why don't you get started?
Okay, great, thanks. Yes. So today I plan to talk about a piece of research that I put out recently, and that was also in the news at the beginning of last month, thanks in no small part to Gretchen. But I'd first like to acknowledge a lot of my collaborators at CIERA. I really couldn't have done this without contributions from scientists at my home institution, and also especially from the young supernova experiment. So this science was really enabled by a very special collaboration to me that studies young supernovae and follows up new transients. But today I'd like to talk about a really interesting transient event, the supernova 2019 YVR, and what's going on with it and why I think it's really kind of an oddball supernova, as I talked about in our press releases. So first, I studied both astrophysics and history in school, and so in most of my public talks, I like to talk about really the history of astronomy. And I think supernovae have really revolutionized astronomy in multiple ways. Recently, of course, because of the discovery of dark energy and the accelerating expansion of the universe with the Nobel Prize in 2011. But there was several previous revolutions in astronomy thanks to supernovae. First, supernovae were really important because they overturned one of the previous models that we had for the universe developed by Aristotle, who thought that the universe was composed of sort of an unchanging, indestructible and permanent sort of material that made up the heavens. But Chinese and European astronomers sort of overturned this over the last 2,000 years through the discovery of guest stars. And I'm showing two of them here, very near and dear to my heart because I started studying supernova remnants early in my career. The Crab Nebula, which was discovered by Chinese astronomers in 1054 and provided this really critical discovery of the timing and the luminosity of this supernova when it exploded about a millennium ago. And then a sort of more controversial discovery by the Astronomer Royal in England at the time of Cassiopeia A, this kind of curious star in the Cassiopeia constellation that eventually exploded and became the supernova remnant that's been very well studied today. So I think this is a really important touchstone for the science that I'm going to be talking about today, both in the historical sense, but also just because it sort of demonstrates that a lot of the science that we do is discovering objects in the changing sky and aspects of the universe that are that we can observe to change in real time. But really the science that I'm going to be talking about started about 30 years ago, a little more than that now, in 1987, with the discovery of a supernova that I'm sure a lot of you are familiar with, 1987A. So this was a supernova that exploded in the Large Magellanic Cloud, one of our nearest neighbors in satellite galaxy of the Milky Way. And really provided us with a lot of important insight into the explosion of massive stars and how they affect the universe and provide the elements and energy and the sort of nucleosynthesis that we understand today. But the study that I like to investigate, and the aspect of this that I find the most interesting is how do the stars that form supernovae, these massive stars that end up exploding as supernovae, how do they die and how exactly are they exploding as supernovae like 1987A? And the way that we understand that is really by going into pre-explosion imaging. As I'm showing here, we have an image of the Large Magellanic Cloud almost immediately after 1987A exploded. And you can see this fantastically luminous source right in the middle of the Large Magellanic Cloud. And then on the left, we go into pre-explosion imaging, as was available at the time in 1987A, and find that there's a very luminous blue star that ended up exploding as this supernova. So this is the technique that I use the most often to study supernova progenitor stars. But we've been able to sort of refine and enhance on this technique in the years since 1987A, the first supernova progenitor star was discovered, in order to find more and more of these examples and study them in detail as supernova progenitor stars. And that's really been enabled by one of my favorite telescopes, the Hubble Space Telescope, which has been in the news a lot lately, and I'd be happy to talk about later. But really almost all of the science that we've done since 1987 has been due to the fact that the Hubble Space Telescope has been observing nearby galaxies and the resolved stars in those galaxies in order to eventually find that they explode as supernovae and then characterize those stars as with 1987A. So this is sort of my rogues gallery of galaxies that I've studied in the most detail. All of these galaxies, what they have in common, apart from the fact that they've been observed by the Hubble Space Telescope, and there's this beautiful imaging that's available in Hubble Space Telescope archives to study all of the stars in these galaxies. They also all have supernovae that have exploded in them, and we've been able to identify the progenitor stars of these supernovae due in no small part to the Hubble Space Telescope imaging. So to sort of cut to the chase, the supernova that I'd like to discuss today and the Hubble Space Telescope imaging that I used to identify the progenitor star of the supernova is 2019 YVR in this galaxy NGC 4666. It's about 14 megaparsecs or 40 million light years away, which of course is, extraordinarily large distance, almost hard to wrap your mind around, but is actually quite a small distance in terms of the overall universe that we've been able to image with Hubble and the galaxies that a lot of us study at CIERA. But the supernova 2019 YVR that I'm pointing out here in Gemini imaging, this was almost the last Gemini imaging that was obtained in the Southern Hemisphere before it went into shutdown due to COVID, and has only reopened within the past several months, and started obtaining imaging in their adaptive optics imager that I used here to identify the supernova 2019 YVR. And we do really need high resolution imaging, which is what we used here to align to Hubble Space Telescope imaging and very precisely identify in some of the most high resolution optical data that we've obtained to date, the progenitor star in this archival imaging. And really, the trick here is very simple. We just align the two images, and if there's a star that lines up in the Hubble data, we consider it to be a valid counterpart star or progenitor star. And so that's not all there is to the science that we do. Oftentimes we have to go back in the Hubble data and verify that the progenitor star actually disappeared, which requires follow-up imaging. But for the most part, that's really all there is to it. And we were able to very rapidly identify the progenitor star after obtaining this Gemini imaging. So what were all of the curious aspects about this progenitor star, and what made it so odd that motivated this paper that we wrote and the eventual press releases? Well, in general, when massive stars explode, we're seeing the outer layers sort of ejected off of the star, and some of the elements synthesized in the interior layers. And so we usually think about this in terms of the shell structure that's been verified in theory, and in supernova remnants like the ones I showed before, Cassiopeia A, and in many, many supernovae that we've observed. This shell structure is a very solid model that we've seen in many supernovae, and we can verify that we see through these layers of hydrogen, helium, and these subsequently heavier elements all the way up to iron, the heaviest elements that's synthesized in the interiors of stars. But one of the really curious things about this supernova 2019 YVR is that it lacked this outer hydrogen layer, likely because it was sort of a more evolved star, one that had very strong winds or a companion that stripped it of its hydrogen layer. And so what data did we use to actually validate that it belongs to this sort of class of stars that lacked a hydrogen layer? Well, this is hopefully one of the only images that I'll show you that is directly from our paper. But there's the spectroscopic evidence is one of the key pieces of information that we use in supernova science. And here I'm showing just one of the key elements in our paper, these optical spectra in wavelength in the x-axis, and then the flux in the y-axis. And I'm highlighting here lines of helium and also hydrogen right in the middle of the spectrum at around 6,500 angstroms. And so really the key here is that the spectrum of 2019 YVR in black lacks a hydrogen line, which is typical of a lot of supernovae. Like another one of that I studied, 2017 EAW, which has this very broad hydrogen line outlined in red, right in the middle of the spectrum. But unlike 2017 EAW, 2019 YVR only has these hydrogen absorption features, or sorry, rather helium absorption features, indicating that we're seeing through sort of an atmosphere of helium right in the outer layers of the supernova. And so the lack of this hydrogen line gives us really striking evidence that 2019 YVR didn't have an outer hydrogen layer when it exploded. It only had the outer helium layer, which we expect from the massive star shell structure. And in fact, we can quantify this directly. So 2019 YVR, because it didn't have any evidence of this hydrogen line, had less than 1/100th of a solar mass, or a mass of the sun in hydrogen, which is significantly less than what our sun has, let alone even smaller stars. And so there's virtually no hydrogen at the time this explosion occurred. And so how does that sort of accord with what we learned from the progenitor star, rather, when we studied it in this pre-explosion imaging? Well, there was this other hydrogenless explosion, which I showed in the previous image, the spectrum of 2019 YVR, which also had a counterpart. And typically we expect these stars to be extremely hot. And so this is, again, another image from our paper, a very famous image from astronomy called the Hertz Sprung Russell diagram, and showing in these sort of colors of the Romanian flag, blue on the left-hand side, indicating the hottest stars, yellow sort of in the middle, indicating stars that are not quite so hot or not quite so cool, and then red on the right-hand side, which are the coolest stars, these red supergiants, as you can see with the red squares. And then on the y-axis, we have the most luminous stars at the top, which tend to also be the most massive stars, and then the faintest stars at the bottom. And 2019 YVR is sort of in the middle of the upper right in this yellow space, indicating that it's not quite so hot or not quite so cool, as in accordance with the progenitor star that we identified in this Hubble Space Telescope data. Whereas the only other example that we've seen of these type of supernovae that lack hydrogen atmosphere are very hot, which is typically what we expect from theory. If a star lacks its outer layer, you're seeing deeper inside of it. And so you're seeing closer to the part of the star that's generating a lot of energy and heat. And so it should be quite blue. And so it's curious that even though these stars have almost exactly the same luminosity, they have wildly different temperatures. And so that's really what made 2019 YVR this kind of oddball supernova. We really had no idea what was going on with it, or why it appeared so cool. But we did come up with a couple of theories in our paper, and that we also discussed in the press. One possibility is that 2019 YVR had an extremely massive explosion before it occurred. which I'm showing here with another famous star that had a massive explosion without completely unbinding the star, Eta Carina, and the Carina Nebula in our own galaxy. It had one of these massive eruptions that let off lots and lots of hydrogen and got rid of its outer layers. And so we hypothesized that maybe 2019 YVR had a similar explosion with shells of hydrogen, which is actually supported by the fact that the supernova ended up interacting with shells of hydrogen long after it died and exploded. A second scenario that we also talk about is that maybe 2019 YVR was in a binary, and a lower mass star, a less massive star, was sort of harassing it and dragging hydrogen off of the outer layers of the star. And so this would kind of need to be fine-tuned in order to explain the fact that it lacked a hydrogen envelope, but appeared very yellow at the time that it exploded. But there are other examples that we've seen, certain kinds of supernovae that sort of appear like this, although in general, they still tend to have their hydrogen envelopes at the time of explosion. And so this is still kind of a big mystery, and one that we're still following up, hopefully with the Hubble Space Telescope if it gets back online, but also from the ground with the Keck telescope and other telescopes that we use at Northwestern. That's basically all I had to share with you, but I'd be happy to take any questions.
Thanks, Charlie. That was really interesting. We do have a few questions in the chat. So first of all, how are these bodies named? I see M and NGC followed by numbers for several of them. I think is a question that plagues a lot of astronomy and how we name things. So if you maybe can shed some light on that.
Yeah, of course. So both the M and the NGC refer to galaxy catalogs. So M is for Messier, a French astronomer in the 18th century who cataloged a lot of galaxies, and actually was one of the first galaxy catalogs using telescopes that had been designed at the time. NGC was sort of a more formal catalog of the galaxies. Not all of the Messier objects are actually galaxies. A lot of them, M1 actually showed at the beginning of the talks, is the Crab Nebula. And so NGC in the 19th century, actually the late 19th century, was a more systematic attempt to try to catalog these large, sort of fluffy, resolved structures that we thought of as galaxies. Although even then, some of the objects that made their way into the NGC catalog are just nebulae or not full-blown galaxies. And so that, yeah, really these are just sort of abbreviations that astronomers use to refer to previous attempts to catalog galaxies or other objects. But yeah, we've had more systematic attempts in the years since then to identify these as exactly based on what they are in the universe.
Nice. Do you ever wish that, because I remember a while ago there was a supernova that had the letter designation COW just because of what order it came in. Do you ever wish sometimes that whatever you're studying has something fascinating like that, like supernova cow, so that it gets more press? Not that you need it.
Yeah, yeah. So we sometimes assign sort of more significance to these letters. So 2018 COW was a very interesting supernova in that it was nearby, but also it had kind of a weird evolution and physical mechanism behind the way that it evolved and got a lot of press. Yeah, I guess I'm fine with just rolling with whatever we get. I'm sure I'll always associate the letters YVR with the supernova. I don't really have any problem with the fact that it doesn't spell a particular 3-letter word or anything. I know it's all kind of arbitrary in the end.
Yeah, that's fair. So we've got a few more questions. One is, what are the chances of having information about the progenitor and then from the explosion. So I guess I'd interpret this as, what are the chances that you see a supernova that looks interesting like this, and you already have observations of the star and spectroscopic observations in the past before you knew it was going to go supernova?
Yeah, there's probably about a dozen of these supernovae every year where we can reasonably put some sort of constraint on the progenitor stars. So we were very lucky with 19YVR based on the quality of the data and just the fact that it exploded in this galaxy. But yeah, it's pretty rare in general, especially because Hubble hasn't actually observed all of the galaxies within sort of the volume where we would reasonably expect to be able to see massive stars individually.
Neat. So is this going to, do you think that the rate of these coincidences, I guess, of being able to go back and look at the progenitor, is that going to increase with something like JWST in the future? Or?
Yes, absolutely. So yeah, I'm part of a few programs to do this with JWST to look at nearby galaxies and sort of establish this archival imaging very early, mainly to look at the supernovae in these galaxies, but at the same time, of course, we'll be able to resolve a lot of massive stars and eventually be able to do this science when those stars explode. Another great opportunity, of course, is the Vera Rubin Observatory and LSST will, of course, be able to get very deep imaging of galaxies in the southern hemisphere. And even though it's ground-based, we'll be able to, really leverage the seeing that we're able to get from Chile and at these high altitudes. And eventually be able to find a lot of these progenitor stars in optical wavelengths.
That's awesome. We have one more question. Why would a binary star pair strip hydrogen off the star, but not helium or other gaseous elements?
Yes, so that's related again to the sort of shell structure I was talking about before. Hydrogen is mostly in the outer layers of the star and is sort of the most weakly bound to the star based on gravity. And so first you sort of strip all the hydrogen off, and then some stars even do have all their helium, or at least most of their helium, stripped off. And so that, we're only seeing the inner carbon and oxygen layers, which is rare, but there are a lot of these stars that we've seen explode. And I even wrote a paper several years ago in 2017 about the progenitor, or at least the progenitor candidate of one of these stars. So it's, these stripped envelope supernovae, as they're called, even though they're rare, we understand less about their progenitor stars and the systems that form them than the stars that have these outer layers, because they tend to be more luminous.
That's awesome. Those are some great questions, everyone. Thank you so much. Thank you, Charlie, for coming on and giving this talk. I guess now we'll do another round of trivia before we hear from Alex. Let's see. Sorry, I'm just pulling up the trivia. All right. So as I said, we have another round of trivia for you. This is going to be another 5 questions. So as before, go to menti.com and enter the code. This time it's 85511615. So it's a different code than the last time. It's always going to be at the top of the screen though. And we'll give it a minute or two. Let's let people join. All right. Something I forgot to mention last time is the faster you answer a correct answer, the more points you'll get. Okay, I guess let's get started. First question, gas giant planets like Jupiter can be thought of as failed stars. How much more massive would Jupiter have to be in order to ignite hydrogen and become a star? Is it 10 times as massive, 100 times as massive, 1,000 or 10,000? All right, 4 of you got it right. Well done. All right, let's go on to question 2. If you scooped a tablespoon out of the densest region of our sun, its core, how much would it weigh? 5 pounds, 50 pounds, 500 pounds, or 5,000 pounds? For reference, if you did this for a neutron star, it would be over 1 billion tons. I don't recommend you do this for either the sun or a neutron star. But... Oh, right. Nobody got it right. Yeah, it's only 5 pounds, and that is how extreme neutron stars actually are. So it's a tricky question. It's more about how unextreme the sun is. Though 5 pounds for a tablespoon is quite a bit. All right, let's look at the leaderboard. Got Dragonite, Bix right behind, Bodie McBoatface and Sakura. It's a tight race. Wow. All right, let's see how the leads change as we go forward. Let's go to question 3. All right, in terms of energy output, supernova can briefly rival the rest of the observable universe. Most of this energy isn't in visible light, but it's emitted in, is it radio waves, gamma rays, neutrinos, or gravitational waves? None of these are trick questions. They're all expected to be produced by supernova, but there is one that we haven't actually detected yet from supernova. An extra hint, that one that wasn't detected is not the answer. All right, time's up. One person got neutrinos. Looks like everyone answered all across the board. Yeah, we haven't seen gravitational waves from supernova yet. I'm personally very excited about the prospect of doing that in the future. All right, question 4. Which element is so rare here on Earth that it was actually first discovered in the sun before it was ever discovered on Earth? Is it argon, xenon, helium, or hydrogen? All right, 3 people guessed xenon, 2 helium. Yes, that stuff in your balloons was first identified on the sun. And it's because it's simply so light that it floats away rather than being trapped in our atmosphere. All right, one last look at the leaderboard for the final question. Sakura is up front with a really close race for second between Dragonite, Bix, Bodie McBoatface, and ET. Shout out to Bodie McBoatface. I really like that name. All right, final question. In order to shed light on the physiological effects of spaceflight, which sort of baby animal did NASA recently launch to the ISS? Is it a human animal, a baby mouse, a baby cockroach, or a baby squid? The hint is that this animal was chosen because there are pathways in their immune system that are analogous to human pathways. So I'm not sure that will help you answer this question. All right, answers split across the board. Squid was the correct answer. It was 100 baby squid were sent up at the beginning of June. I believe they'll be frozen before they're sent back. I don't know if that's for scientific purposes or to prevent any like mutated Cthulhu-like creature that they create from coming and destroying Earth. All right, let's see the final scores. Bodie McBoatface picked up the points on that one. I think that's enough for second, but not quite first. So first place goes to Sakura, and then second to Bodie McBoatface. All right, good job, everybody. All right, and with that, I'll bring on Alex to give his talk. Alex.
Thank you, Chase. All right, so let me share my screen. That's not what I want. Okay. Y'all see my slides, right? Not like an infinite YouTube stream. Well,
Yeah.
nobody's complaining. So, all right, let's go ahead and get started then. So my name is Alex. Like I said, I'm a PhD student at Northwestern, and I study the invisible universe with computer simulations. And so this evening, I will tell you what I mean by that. So first, I have to figure out how to advance my slides. First, I have to show you a picture of the visible universe. So this is the visible universe. This is an image of our very own universe. Taken, it's a long exposure photograph of a seemingly empty piece of sky. The camera was just pointed at some black spot and left to sit on for, I think it was like a couple dozen hours of exposure, if I remember correctly. And the size of this piece of sky was about 1/10 the size of the full moon. And in it, there are thousands of different objects, right? So we look at it with the naked eye, we see nothing. But if you stare at it long enough, all of these different resolved, big, fluffy things, like Charlie was saying, start cropping up. And each one of these objects is a galaxy, each one with its own size, shape, and color. And so what my research is focused on is, why are they different sizes and shapes and colors? Why aren't all galaxies exactly the same? What makes them different at all? Shouldn't they all just, like, gravity works the same everywhere? Shouldn't everything just kind of form the same kind of stars, and look exactly the same? And so, I think if you were just looking at this image, that question would seem, really hard to answer. And I think that that's for two reasons. Number one, you can't see everything in this image. And number two, you can't watch anything. So what do I mean by that? So you can't see everything. So there are invisible components to galaxies that we don't see when we stare at a dark patch of sky with a camera, just with the shutter held open. Now, some of you might have heard of dark matter, but that's actually not what I'm talking about right now. I'm talking about the invisible gaseous component of galaxies. And so you might have seen pictures of, like, the Milky Way with, like, these dark streaks kind of through it. I'll show such a picture in a second. And that's the stuff that we're talking about. And it's that stuff, which is literally rocket fuel. Okay, it's hydrogen gas just floating around out in space that will eventually turn into a star. Okay, and it's this gaseous component that we can't see very easily, but can be really important in terms of determining the size, shape, and color of a galaxy. And then the other conundrum is that we can't watch anything. So we're looking at this still image, and we can't see how it's going to evolve. We can't wait billions of years for one of these galaxies to change or grow or do whatever, and then check in on it again. We only get to see just the one moment in time. And so what people will try and do is look at different galaxies that are different distances away. And what you can do is say, well, because it took some amount of time for the light to get here, right? Light travels at a fixed speed of light. And so if something's 8 light years away, it takes 8 years for that light to get here. If something's 2 light years away, it only takes 2 years for light to get here. So you can look back into the past by looking further and further away, thousands and thousands of light years, millions of light years away, you start hitting these galaxies. And you can try and make a connection between a galaxy that's 1 million light years away to a galaxy that's 10 million light years away, and then say, oh, that galaxy 10 million light years away might over the course of time, evolve into the galaxy that we see now, or a galaxy like it, a galaxy analogous to it. And maybe then we can kind of convince ourselves that we're watching it. But really what you're doing is you're looking at a family photo and you're trying to draw a connection between cousins, right? Cousins of different ages. They're still going to be different, right? Each cousin has lived its own life and done all sorts of different things. And maybe there's something that's the same about them, but you can't really draw, the connective line. And so these are two really difficult challenges to overcome in the real universe, but not so in the simulated universe. And so before I continue, I have to admit that I've lied to you already, is that this is not a picture of the real universe. It is a picture of both the real universe and a simulated universe. So split on the left side and the right side are images, the so-called Hubble Deep Field on the left, made from the real Hubble Space Telescope, and a simulated version on the right, where we've run a computer simulation and then pretended that there was like a little Hubble Space Telescope in it, and then simulated what the starlight would look like from some random position in the simulation. And the nice thing about a simulation is that you can see everything, right? So anything that you put in, because it's all computer code, right? You, excuse me, you know what it is. You can go and you can look for it. You don't need a telescope, you just have to make a picture. And you can watch anything. I mean, you can watch everything if you wanted. I mean, there's a lot of objects, but you can certainly watch any one of them grow and evolve over time. And so simulations can be really powerful tools to understand why galaxies look the way that they do. And because these simulations will produce a realistic population of galaxies that, to the casual observer at least, you can't tell the difference here. I would say that they really offer a valuable tool to shed light on some questions that we have about the real universe, even if they're only a simulation. But let me talk about that for a second. So, what I was showing there was a big zoom out of a whole bunch of different galaxies, but you could zoom all the way in on a single galaxy and really simulate it at high resolution and answer a lot of different questions about galaxies like the one that you're simulating. And that is one such galaxy that I'm showing here from the FIRE simulation. So I'll come back to what that means, but that's the collaboration that I'm a part of. And on the right is what we were looking at before. That's the visible part of the galaxy. There's some starlight, maybe you see a little bit of dark streaks going on, but then on the left is the invisible part. This is the part that's the gaseous component that's going to eventually form stars. You can see that there's a whole bunch of stuff, this green streak of cold gas that you don't even see, or this clump here, they just don't even show up in the image. But this stuff will eventually merge and join into the galaxy and become stars. And the amount of gas that's coming in and the way that it's coming in can determine the size, shape, and color of the galaxy. But I promised that we could watch anything. So that's a picture. That's no fun. Let's take a look at the video. And so this is taking that same picture and just putting it into motion. What you can see is that in the simulation, we get this remarkably beautiful view of a galaxy growing over time that we never would have anticipated. This is not a galaxy that's just a happy little disk that's spinning around, doing its thing, looking like the Milky Way. It's explosive and violent and beating like a heart. And it's something that we would never know because we can't watch. We only ever see galaxies, in a snapshot in time. You'd have no way of knowing. But as you can see, is like over time, eventually it does start to settle down and become this beautiful, twirling, happy, I like to call them happy little disk. And so this is really the power of the simulation that we never would have been able to answer just from looking at still images. So hopefully I've convinced you that, get the slides back, that the simulations are worth looking at, that they can really start to answer some of the questions that we have. What questions, though, do we know? That's the end of my talk. Don't look, everyone close your eyes. I like scroll very strangely with my trackpad when I turned on the annotations. And then it did that. I don't like that at all. Okay, so as I was saying, the simulations will produce this incredible sandbox where we can go and we can ask whatever question we want, really, about a galaxy, and get an answer that at least we can start to interpret. Again, there's this layer of abstraction. It is a simulation, of course, but the ingredients that we put in are very simple, right? The ingredients that we put in are gravity. We know how gravity works. The ingredients that we put in are fluid dynamics. So this gaseous component flows just like water does, not just like different Reynolds numbers, but I mean like that they obey the same mathematical principles, the same hydrodynamics applied to water, liquid, or some fluid, apply to gas and space. And so these are very well understood physical principles. And then, we make some approximation for the astrophysics that we think we understand, like how stars will evolve. And very importantly for the FIRE collaboration, which stands for feedback in realistic environments, is feedback from stars. And so when a star gets to the end of its life, as Charlie told us before, some of them will go supernova. And you'll have this expanding shell of material that can sweep up stuff in the gaseous component of the galaxy and provide like a feedback process that tells the stuff that's going to turn into stars, whoa, here's a little bit of a push back out. Gravity wants to pull this stuff back in, and we're going to give it a push back out. And the different ways that stellar feedback and star formation can affect galaxies can change their size, shape, and color. So on the left is a blue disk galaxy where there's a lot of young, hot stars, so they're blue, that in bright spots where you might find a supernova. That's a star-forming galaxy with a lot of gas. And then on the right is a so-called red and dead elliptical galaxy where star formation has almost stopped entirely. There's no gas, there's no blue stars. All you're left with are the lower mass, cooler stars that live longer, because the heavier you are as a star, the quicker you have to burn up your fuel to support your own weight. So it's a very like live fast, die young lifestyle for massive stars. So I was talking about this feedback cycle. And so this is in particular what I study. This is going to be, I think, the last thing that I cover in my talk, and I'd be happy to answer questions, is this feedback cycle. And this is something that we've really come to appreciate over the past maybe decade as being the biggest thing that we don't understand about galaxy formation and the way that galaxies grow and evolve. We have this picture of how feedback works, and I'm going to draw it for you, but the exact way that each of the arrows in this diagram work, that's an active area of research and what I spend a lot of time thinking about. So number one, I want to introduce the interstellar medium. So I keep calling it like a gaseous reservoir. So all that means is that it is the medium, the stuff, that is between stellar stars, the stuff that's between stars, interstellar medium. So it's made up of gas that's going to form stars. So that stuff in the ISM will, much like water or the water cycle, will condense into these little clouds that eventually gravity will be so strong that they're going to compress these clouds in the interstellar medium. So you have like a little teeny overdensity of stuff. You get a whole bunch of gas kind of collect onto it because gravity is pulling it in. And then that's going to turn into a cloud that becomes gravitationally unstable. And then it's just going to collapse. And when it collapses, as it's collapsing, it gets hot at the center. And wow, what do you know? You form a star. And so in an individual molecular cloud, you can get quite a number of stars. I mean, depending on the size of the cloud, you could form an entire star cluster of like hundreds to thousands of stars of all different masses. And, and like I said, masses means different ages and colors and things. So you can get a whole bunch of different stars from a single cloud. But in this picture, let's just pretend we're getting one star. So this star, gravity eventually pulls it to the point where nuclear fusion is triggered. And then nuclear fusion turns on, and then the star supports itself by burning up this rocket fuel, turning it into helium, and then from helium to carbon and oxygen, and then into silicon, and then into all of those different shells that Charlie was showing before until you hit iron. And then once you hit iron, that's bad news for the star because you can't burn iron in a star anymore. The atomic physics is such that it actually costs you energy to do that. And so you eventually run out of fuel and nothing is stopping gravity anymore and everything collapses and boom, you get an explosion that can briefly outshine all of the stars in a galaxy. Which are billions of stars in a galaxy, one single star that has run out of fuel can, in its last gasp, its final show, put on quite a performance. And that supernova will, as I mentioned before, take a shock wave. It will be this huge explosion that just expands through the interstellar medium, which will stir it up. And it can disrupt the formation of new giant molecular clouds. And so there's this delicate balancing act between the rate at which you're forming stars, the rate at which they're dying, the rate at which those stars are stirring up the interstellar medium. And we call this a self-regulated cycle of star formation. And so in particular, the arrow that I spend the most time thinking about is this feedback piece, is how turbulence is generated in the interstellar medium and how that's related to when stars die. Because stars can provide feedback in other ways, like through stellar radiation and through stellar winds during their lives, but it seems very important that something like 90% of the feedback that they produce in terms of preventing new stars from forming is coming from these supernovae. So the last thing I want to leave you with is that this feedback is really important in determining the size and shape and color of a galaxy, and it can be really important in totally shutting off star formation altogether. If feedback overshoots, it can totally evacuate the ISM of the galaxy. That's kind of what we're seeing here. So in this galaxy, you should see these two like biconical, like red spindly things. That's X-ray emission from hot gas that's being thrown out of the galaxy from stellar feedback. And we call this phenomenon galactic winds. And in galaxies with a very high star formation rate, where they've sort of formed almost too many stars, then those stars eventually die soon after, and then just those overlapping shock waves can totally evacuate the galaxy of star-forming material and shut down star formation. Once you've shut down star formation, then you don't have any more blue stars, and hey, what do you know? Your color has changed. So just really to drive home the point is that feedback is really key in understanding what drives the size, shape, and color of a galaxy. It's something that we've learned about. And so if you've enjoyed this talk and you're curious to play around with our simulation data, we have it hosted online in this visualization tool that I built called Firefly. You can find it on my website. And what you can do with it is flip it around, spin it, apply filters, look at the data, and there's a bit of a hidden Easter egg in the data that I showed. You should be able to find some biconical outflows if you play around with the filter parameters correctly. If you're having trouble, I'm pretty sure on my YouTube channel, which may or may not be linked on my website. I'm revamping their website. It will be soon. I have like a tutorial video on how to suss them out of the simulation. But anyway, with that, I've talked quite a bit. I'm happy to take any questions that anybody might have.
Thank you, Alex. That was really awesome. I can say I have played around with that tool a little bit. It's super cool. And you've also done that you've implemented something with Firefly, I guess, at Adler.
Yeah, oh, that's a great point. Yeah, so we have at Adler, well, back in the olden days, in the Space Visualization Lab, we set up Firefly in so that you could do this same activity of zooming through it and trying to find the biconical outflows in like this interactive format on one of the wall screens. Yeah, in Adler. Yeah, I don't think the SVL is open right now, but I think the planetarium is opening up soon, if not already. But I'll find. Yeah, I'm still working with the planetarium, so yeah, I will certainly.
Yeah, I just wanted to give that a shot.
Find out.
It's really neat.
But yeah, thank you.
One day when we can all go back to the planetarium, hopefully people can check it out. We do have a question in the chat. I hope people are still. Yeah, you should still feel free to post questions for Alex. So one question, I think this is from the beginning of your talk, regarding the deep field photo you showed, is how do you do a multi-hour exposure? I would think that the Earth would eventually get in the way.
Yeah, no, that's a good question. So certainly the Earth does get in the way. And so what you end up doing is it's not like you're just keeping the camera open for 24 hours or whatever. I mean, Hubble is zipping around the Earth. I should know the time of orbit, but I'm pretty sure it's less than a day. I think it's a lot less than a day, like a couple hours. So it gets in the way pretty frequently. So what you're doing is you're taking short exposures and then stacking them on top of each other, and then you end up with like a total exposure time of some number of hours. Because if you just held it open, then like another satellite would go by, that you get in the Earth like a bajillion times. You know what I mean? So yeah, I think that they do like a couple minute exposures and then stack them. But I'd have to check. I think that's explained somewhere, like on the NASA website where they talk about the deep field.
Yeah, that's a great question. Also, Mary wants to shout out your analogy. I think this is your water analogy, your hydrodynamics analogy for being good. I definitely agree.
Thank you.
I do have to say that deep field photo where you split it in half and say actually half of this is a simulation did not do anything to help ease that paranoid part of your brain that goes, oh man, are we all living in a simulation?
Yeah, I've gotten that question a couple times. It would have to be they'd have to be very good programmers. Let me tell you. There's a lot. So for example, in the simulation on the right, the smallest thing that we can resolve is something like 70,000 solar masses, right? So we're talking the smallest thing you can resolve is an individual star cluster. And it was very expensive to run the simulation on the right. Okay, like very expensive, both in terms of like electricity and like computer time, but also, cold hard cash. And so to get all the way down to like atoms and stuff and simulate that, I wouldn't even want to know what kind of computer we're living in.
That actually brings me to my next question, which was, what are you using to simulate this? I take it you're not doing it on your laptop. I know you
yeah, no, I'm not doing it on my laptop. So the way that this works is there are like national lab facilities that will build these supercomputer clusters where we'll run the simulation. There are also technically separate, but like philosophically the same, I think. Computing facilities that are run instead of by the national labs are all by the Department of Energy. There are computing facilities that are run by the National Science Foundation, and they'll also have these huge server racks, where the supercomputer lives, and then you submit a proposal and you can use it. But there's also something, I was talking to somebody many years ago about trying to outsource some of this, like crowdsource it, and use people's cell phones to crunch some of the numbers. And that with enough cell phones, you could get the computing power. The question is just how do you distribute it? And can you piggyback it off of other network communications? Because people are already using their phones a lot. And so it was an interesting idea. And then, you end up watching like Silicon Valley, and that was exactly the game. So I thought that was curious. But yeah, I don't know. But I don't know if that's the future. But at the very least now, yeah, basically you take a whole bunch of CPUs and you duct tape them together, and you call it a day.
Nice. Yeah, that blows my mind to even think how you would do that, given how, I don't know how parallelizable the problem is, especially because you're talking about feedback, and especially this problem where things happening in one place are happening or affecting things happening in another place at other times.
Yeah, it's a big problem when we're running these simulations, is trying to split up the domain and make it parallel. But the codes are pretty good at it. So we'll typically run on a couple thousand CPUs. And most codes will scale pretty well there. Some of the like much larger simulations, like this one, they'll get up to millions, of computers all talking to each other, and it's just I can't even imagine. I'm so glad that I've never had to run a full machine job, because like for that like 2 weeks you're on call 24/7. If one of the node fails, it could totally ruin the entire experiment.
Yikes, yeah, I would not want to be that person. Cool, well, looks like we don't have any more questions. So with that, I guess we'll call it a day. Thank you everyone for showing up. Thank you, Alex and Charlie, for your great talks. We do not have an event planned for July. We're going to take that month off, but we will let you all know when we're returning. Also, I want to shout out that we will have news in the future about in-person events at the Dearborn Observatory, where you can actually do some observing and then come and hear talks in person and not over Zoom with all these technical problems and muted audio and things like that. But anyway, with that, I just want to say thank you all and hope to see you soon. Bye.